Simon Birrer is currently a postdoc at Stanford, and he'll be moving to Stony Brook beginning next year. And Simon is going to give us a little glimpse into the analysis of strong gravitational lenses.
Somewhere there we are. Okay, share screen.
And it looks great on the Zoom, so Simon, take it away whenever you're ready.
Thank you very much. So it's a great pleasure to be here. Thank you very much for the organizer, Gautam, really much appreciate. My job here is basically give an introduction, reflecting maybe back of what we heard of all these great talks on strong lensing. There's still some to come that have strong lensing components, and look a bit back, actually, what do we measure and how can we use it moving forward? A lot of people have talked about large populations of galaxy or strong gravitational lenses we're going to find, and I want to spread here a bit of ideas, thoughts, and cautionary notes of how we can move forward here. And this is meant for the broad audience, so if you have like questions or so on, please come to me or any other person that presented on strong gravitational lensing. To start with here, this is the image that you may have probably have seen, galaxy cluster. You see a lot of these fancy like little things. First I thought like my screen is dirty, but these are actually little spurts of strong gravitational lensing feature. In particular, the very little ones were the ones that I was very excited about because I was not aware that they're there. And so the question is, how can we use this type of data? What can we learn from first principle? When we have, let's see, this is basically the problem that we have in a nutshell in a forward modeling. So there's some intrinsic source behind that we don't know about. It's being lensed here, it's distorted, and then convolved, pixelated noise, so all what our instrumentation does, and we see this blurry thing, and we ask ourselves, well, how can we learn about these distortions here? And what part of that distortion that here is applied in the computer can we get back when we look at such an image? And this may look like magic, and so I try to mystify part of this process that many people have talked here about. So first, from like dry theory, what can we measure and what can we not measure? And what makes strong lensing so unique that so many people are actually using it? And the difference between strong lensing and weak lensing is that we have multiple images, at least two. And so for example, here on the left, you see this blue, these two blue images. We know they come from the same source. It can be either S or S tilde, we don't know. But what we can really know is the relative distortion between this image and that image here. We know the relative time delay we can measure, the relative position where they are, so the relative deflection angle, and the relative higher order distortion. This is really the information we have accessible, regardless of what the source really looks like. If we want to make more assumption whether we think the source looks more like S or S tilde, we can learn more about that actual lensing transform. But the between here, T to 1, basically the inverse of 1 times the other, that relative transformation here is really the thing that by the data we have accessible without more assumption. It's just about the data quality, how well we can measure these aspects. What has been mentioned many times is the mass sheet degeneracy. This is very relevant for Hubble constant measurement. And what it basically means here, and then the generalization that you may not have heard so much is called the source position transform. And in short, the source position transform is this image where we can just reshape the source in any other way and find another transform in both direction that satisfies both images in brief. The mass sheet is basically when this transform is a scalar, when you just make the size larger or smaller. That's just the simplest version of it. And the way you can think of it here, a bit of math, bear with me. If you have an image D, it is what is the source, and then gets operated by the lens, so you distort it. So you operate on the lens. What we can do is we can do the unitary operator in there and just put any bijective transform in between, and then say like we shape the lensing operator slightly different, and the source is slightly different, and we get S tilde or L tilde, and these are these two parts that we cannot distinguish. This is the broad mathematical, all the degeneracies basically are covered, and now you can think of what this is. If this is a scalar, this is the mass sheet transform, this is just in that form. You can linearly distort it, you can change the shape. Some people that do weak lensing are very well aware of that. It's called the shape noise, so you don't know that. What we have a difference in strong lensing that we have at least two sources or two images, and so the relative shape is really accessible. And then we can have higher order ones that I'm not going to talk about. I'm not sure there's really a name for this, but you can expand this further. But this is kind of like the mathematical thing if people talk about lensing degeneracies in one or the other way. So coming back for the source structure. So in any modeling, when you see imaging, you need to either make some assumption on the source, or at least know, well, this can be very complex structures, like Spire Galaxy, we see beautiful images. And so there are many solutions to those. And so how do we do that in practice? And one way here is to do a linear problem or a semi-linear problem. So whenever possible, if we can phrase a problem in a linear equation, we can do a matrix inversion and get a solution for it with the uncertainty. And that's what many of these codes or techniques at the end do. And here's just one example when you use as a linear basis set shapelets, which kind of like look like these weird things, polynomials, Gaussian drop-off of Hermite polynomial. You can use pixel, you can use Fourier mode. It's all up to you. The fact is, none of them looks really like a galaxy, but if you superpose many of those, you may come close to a galaxy. That's the idea. This is in the source plane, and what you can do is like you can lens any of these components independent of each other through your lensing kernel, apply the convolution and pixelization, and you get basically a mode in the data space. And now you can ask the question, what linear superpositions of those blurry, weird sets gives the best fit to that data? And you get a solution for the components, coefficients for each one of them. And then you evaluate them in this plane, and you have a source reconstruction. And that is for a given lens, proposed lens model. You get an idea of what the best fit to your data is. And you propose another lens model, you do the same thing, and so forth and so on. And it's up to you how complex you choose your source, your regularization. We also heard a nice talk by Shachib, Adam, Legends that have different descriptions on either side of dealing with that problem. What I want to show you is a movie here. This is not just in praxis or in theory, but here this is a movie running inversion, lens inversion, with n-max is the polynomial order in the shapelets, and each time this runs up, it does a full linear inversion. From this is the input image. This is how it's being reconstructed. And this is the reconstructed source when this was the true source. And you see, by about now, you fit the noise. And probably by now, you start overfitting your data in that sense. Here, I pretty much cheated. So I knew the input, and the lens model was the correct one. And so at least for the correct lens model, even if I had no clue about the source, it looks fairly similar to the noise level. I can do the same exercise by hiding some or distorting some of the lens model that in the output we don't know. And I run this movie again. So it's a very similar lens model that I do the reconstruction, but it's not the correct one. And at first, everything looks great. We get the main features back, the arcs, here the distortions, but something here just remains. And no matter whether we add complexity in the source, it just stays there. And what stays there is a feature in the lensing kernel that no matter how much complexity I add in the source cannot be overcome because of the relative distortions just don't add up. No matter what I do in one side, I cannot compensate on the other side. And what you see here is that hardly to see is there are not just here a bit of residual, but they're counter-residual here and down here. Because of the multiplicity of the image of the same source, you cannot at the same time do both. And that's a sign that this lens model is not the right one, and we have to propose another one that gives a better solution to the data. That is basically the idea behind lens modeling, to come up with something that matches in that regard. So, the next, I'll show this image here back again. So you see these beautiful arcs and these little arclets, etc. And you can think of locally describing lensing or globally, and there are different techniques here. And when locally, the first order is shear, but if the lensing gets large, shear itself is not enough. You need to go to higher orders. The next is deflection. But there's also another basis you can use that actually leads to so-called arclets, that actually curves the right way that flexion does not. And you can describe a continuity from no lensing to basically weak lensing. That's what our folks in large-scale structure do, to basically all the way to strong lensing, and some of those things may sit more over here in terms of stretch and how it's being curved. Just give you an idea. And the question I have, how can we maximize lensing information in future surveys that find different types of lensing feature beyond the linear regime? And what I also want to show here is, don't just think of this regime and nothing in between. It's continuous, and the strong lensing is just the strongest selection effect we have on the sky in terms of lensing. When we do modeling, or you can do multiple choices, and it depends on the investigator and what type of science you want. And when you do choices in your mass profile, in that sense, you have to be aware of what you're actually measuring and what you imply that you don't have access through the data. I talked about the degeneracies on one side, and here I want to give a bit of glimpse of what we actually can detect. And this arclet definition that may help to see when we have an elliptical mass profile. So around is all spherically pointing, all the arclet looks the same. If the mass distribution is elliptical, you see that the stretches tangentially changes as a function of azimuthal structure. When there is a shear distortion coming from large-scale structure, it changes the direction of these arclets in one or the other direction, as an example. And there's ways, depending on how good the data is, that you can distinguish these different parts, and you can fit in one lens model and it doesn't match, or you need extra components to be fit. So this is the azimuthal structure. Then radially, so radially means in terms of like, as a function of radius from the deflector center, what is radial observables we have? We can have like different image position asymmetry, or how, as a function of radius, these distortions actually change. And there are different power laws that have been modeled here, and it's very hard to see, and this is not by surprise, that these distortions are slightly different, but they're very, very similar. So it's a very subtle effect here. When we have enough data, we can actually perform and getting a radial differential of our deflectors at the Einstein radius, or where we have the data. And often in the literature, power law elliptical profiles plus shear is kind of like a standard that's been used to model. And for me, I think that way is like that such a model, simplistic, is effectively an efficient way to extract local properties of what we can observe. So it has enough degree of freedom to describe these phenomena and a bit of a radial degree of freedom. But it doesn't mean it has actually to be the correct model. But it's a way that's been used very commonly. So then the question, so zooming out, so this was a bit in the theory, going very into the details. Now I go on the opposite side. So I leave all the amazing work that's been done in analyzing and actually having constraints out on the Hubble constant, on dark matter that we heard from many of you guys here in the audience. But now I go on the other side, like what can we do with of order 10,000 lenses? And what I want to emphasize is that basically going away from single objects cosmology to full covariant joint analysis in the cosmological context. Think less about the individual lens, but what the sample gives us. And so when you think through in terms of what people have done in weak lensing, large-scale structure, etc., you can think of weak lensing cross strong lensing. So it's not galaxy weak lensing, it's a weak lensing, a strong lensing, as an example. Galaxy strong lensing, it's not galaxy lensing. So how are they covariant? Strong lensing tomography, so how do the Einstein radius change as a function of source redshift, as a function of lens redshift? That's basically this pseudo-multiplane lensing, if you put it in that extreme. We heard from Eric Linder and a student. And so how this has been done? How can we use these arclets, flexion chip? Around since I think more than 2 decades, arc statistics is just a broad umbrella of what these things actually do. And what I also want to ask is, aside from the Hubble tension, can we probe sigma 8 tension in that way? Structure growth, alternative theories of gravity, dark matter particle nature, galaxy formation, etc. So what kind of ways can we actually go and use these types of observables? And how to be prepared after all. And here's just an incomplete list of tasks for a bright future. So I'm very positive seeing the energy and what people do here really. And I just want to emphasize a few things as of why I'm here personally and need your help, or we need your help in that sense. We need to understand the whole transient sky to look for rare events. I have no idea what's all blinking out. You guys know that much better. I just know when we go for a very rare event that we have to understand everything else that we can actually target and find this. Test on current real data and end-to-end data challenges. Current real data, and we have seen from Jimena and from others, is really a test bed for how realistic are we doing our analysis and search. And exploring the continuity between strongly lensed and the unlensed supernova. So the strong lensing is just, quote unquote, the extreme selection effect in a population distribution. So all the supernovas are lensed. Mostly that are local, not very much, but somewhere we meet halfway in between where we want to care for it. Is it a signal or is it noise? Then what we heard a lot is machine learning versus forward modeling, and interpretability of machine learning versus slower speed of forward modeling. And for me, like foremost is understand what we measure. So if we go to very large samples, we get a lot of precise information, but what are we actually measuring, what is extracted? And I caution in that sense a bit the machine learning. I'm super excited, but also want to see a push in that direction. Then, I'm not sure it's been mentioned, but I think it's common to be mentioned. Do we rely on photosees or most, or can we find spectra for a lot of aspects? And then selection effects, selection effects, selection effects. Strong lensing is a selection effect, and if we're not talking about selection effect, when doing strong lensing analysis with a large sample, we're doing something wrong. So I mentioned that before. We showed, like Jimena showed, a certain cut when you do the searches. So searches and analysis should be within one umbrella be treated. And sometimes we may even have to rediscover old lenses when we know actually, okay, do we propagate all the uncertainties? The current lenses, I personally cannot reconstruct the selection function or all of them because they came from so many different surveys and people and luck and chance and whatever. LSST will change that we can rediscover all of them that we need in a uniform way. And watch out for surprises. That's kind of like the last message here. I'm not as smart as I pretend to be sometimes or often, and there may be things that we find in the strong lensing or in other things that we have not anticipated. And I also cannot really tell which methodology is the ones that leads to the best results. And given the time is up, I say here, thank you very much, and I leave it with that.
Thanks very much for the awesome talk. Maybe more of an epilogue than an introduction. I feel like I need to go and rewatch those ones you talked to. Does anyone have any questions for Simon? Remy?
Thanks, Simon. Great talk. Selection effects, selection effects, selection effects. Do you have a sense for how to reconcile the awesome power of having machine learning being able to do the detection and at the same time being able to characterize their selection functions just because of how uninterpretable they are?
Yes. Fortunately or unfortunately, I have a slide on, or actually too many slides on those. This is work by Ji-Won Park. So what we see here is these dots here represent galaxies at different redshifts with different masses, and the lens is somewhere in the center. And so when we see the light on the sky, the structure, we want to interpret on what kind of like over or under density a certain lens is. We have a catalog of information that is incomplete. We would like to know what the dark matter underlying is. And in that kind of regime, I think machine learning is very advantaged to actually filter out what is the information that's actually needed that we can reconstruct the environments. And so that's what we've done here on a population level, is Bayesian graph neural networks in that sense being applied to learn about, well, what is the convergence field here in the center where we are interested in a lens in our case. But this may also be technique relevant to supernova just at high redshift, right? So that you have a magnification bias that you may also study in similar ways. So that's kind of like my short answer of something that's being worked on. Yeah, an answer in the little advertised too, this works.
Nice, thank you.
Other questions? Many, okay.
So regarding your point about interpretability versus time budget, so forward modeling. So we'd like to think about tens of thousands of new lenses, but what do you think will be the fraction of these lenses that will require the detailed amount of modeling that will make up for this time budget? Or do you think that will not be the bottleneck?
My personal view on this, there's probably not one size fits it all. So there may be methods that can deal with all of them, but in a very crude way, but still being accurate and precise. And other methods are better having a gold sample, where you look for the 1,000 most relevant and analyze them more. And I think there's space for many different ways of approaching that. And some method we've seen is more going to the 10,000, others to 1,000. You know, this is already, you know, any of those is e-folding from what we have now. So there's not a one size fits it all, and there's definitely a degrading, and as you said, degrading in quality when we go to 10,000. And so it's the question of what you want to deal with in terms of systematics. Say again?
About 10%.
Yeah.
Thanks, Simon. I had a question. Well, I don't really have a question. I'd like you to talk a little bit more about photoses. Yeah, I'm just curious what you would say about. I mean, it just seems obvious that they kind of need to be used in the near term, but I'm a little skeptical at how well we'll be able to utilize them. So I'm just curious if you could talk a little bit about that and whether it's going to end up being better to just sort of like have a smaller spectroscopic sample and just sort of ignore them, or really need to put some work into the photoses in order to use them.
Yeah, my optimistic myself would say like 10,000 sources is not out of the box of putting spectra in if we go big, or having a significant number of those that caught a certain magnitude threshold. And so be a bit bold and say like we want to have most or a significant part of that with spectroscopic redshift. That would be my dream. And then having a check whether the photosy is good enough. For the photosy, we would definitely need a handcrafted pipeline of doing the deblending between lens and source, which I think is currently not like the default in this crowded environment. And so it's going to be a mix between lens modeling and photosy simultaneously doing, and how to propagate information. People have thought, I know that this is not my idea, of combining Euclid and LSST, so that you can, with Euclid, you can do better deblending of higher resolution, but not the bands. And so a combination of Euclid and LSST I see a very promising of utilizing all the samples. LSST alone photoses will be a systematics that we would have to find, for sure.
All right, thanks, Simon. Let's give him another round of applause.